Good afternoon, one and all. Respected Dr. G.K. Day, former Director, Materials Group, BRC, Professor U. Kamachi Mudali, Honorable Vice Chancellor, HBNI, Professor P.D. Nayak, Dean, HBNI, Professor B.K. Datta, Professor Tyagi, and other distinguished dignitaries present in this hall and online, faculty members, students, and other participants. I feel privileged to extend my warm welcome to all present for Dr. Srikumar Banerjee Memorial Program. We are privileged to have Dr. G.K. Day, former Director, Materials Group, and speaker for today's Dr. Srikumar Banerjee Memorial Lecture. Today we have gathered here to mark the second anniversary of Dr. Srikumar Banerjee, former Chancellor HBNI, which to be precise fell on 23rd May, and due to certain constraints we are organizing this event today. Dr. Srikumar Banerjee was a remarkable person. He was a great scientist, engineer, technologist, policymaker, intelligent analyst, strategic thinker, excellent speaker, and research supervisor to many of us. He stood strongly for indigenous technologies and was a great motivator. Many of us have known him for much longer and worked with him much closer. Now I'd like to request Dr. G.K. Day, Professor Kamachi Budali, Professor P.D. Nayak, and Professor Swain to occupy their distinguished chairs, please. Yes. I would like to request Professor U. Kamachi Budali, Vice Chancellor HBNI, to welcome Dr. G.K. Day by bouquet of flowers, please. Thank you, sir. Now I'd like to request Dr. P.D. Nayak to give welcome address, please.
Good afternoon, and thanks for joining HBNI Dr. Srikumar Banerjee Memorial Program. This program is organized, this is the second first organized to remember the contributions made by Professor Banerjee in various domains, especially as Vice Chancellor of HBNI. He was guiding path for of us at HBNI with his innovative ideas and always pressing us that we should make HBNI one of the well-known institutes, not in India, but in international arena. He is no more with us, but his guidance and its teaching will always guide us to save the HBNI in coming picture. As Surya mentioned, he has contributed not only in science, but also in the academic sense, and also as a secretary in administration also. And its simplicity and way to mix with anybody, maybe at any rank, has always touched our hearts at many times. He's the most approachable person at any time and ready to discuss any topics, not only connected with material chemistry, but any topic you'll be given. In fact, we were invited to many times for chemistry. There also he'll be address the gathering or brief the gathering about the chemistry, telling that chemistry and chemistry they are almost same because anywhere the electron transfer or all the things are involved. The same thing, maybe sharing of the electrons, the transfer of the electrons. You see, finally, it is the chemistry, the game of electrons. We are not going in deep inside the nucleus, but only the outer electrons, which are the gravity of the chemistry. and he is quite aware of that. I now, on behalf of Umivawa National Institute and on my own behalf, welcome you all, and also many dignitaries who are present online for this program. We have connected to WebEx as well as T2. I welcome them. I welcome Professor Dr. because Dr. J.K. has contributed heavily for our academic programs of HBNA also. Like Banerjee is a well-known metallurgist and contributed not only in the BRC vision-oriented programs, but also strongly in the basic science, especially in the material chemistry and material engineering. I welcome you, sir, and thank you for accepting our invitation to deliver the lecture today at this occasion of Srikumar Banerjee reviewing balance. Our Honorable Vice Chancellor with us, he joined on 11th of May as a VC HBNI, Professor Kamasri Mudari, and is guiding us in various ways now, and has long vision to take HBNI till further right. And I wish him all the best, and we are always to help him in whatever way we can able to do that. I welcome my colleagues and other dignitaries present here. Professor A.K. Dureja, organizer of this function, head HRDD and associate dean. Dr. P.C. Selvin, Professor A.K. Maiti, A.K. Tyagi, Director Chemistry Group, Professor Ghosh, Professor Pal, Professor Nayak, Dr. Susingar, Dr. Datta, Dr. P.K. Datta, we have not Datta with us now, and all other my friends and colleagues here. Professor Srikumar Banerjee was one of the greatest metallurgists of India and also known in the international arena. He served as the chairman of Atomic Energy Commission of India and Secretary Department of Atomic Energy, and before that as the director Atomic Energy, Baba Atomic Research Center. After his tenure as a chairman Atomic Energy Commission, he served as a DAE Omi Baba Chair Professor at BARC Mumbai. As we lost him, and we are expecting many more advices from him. It is unfortunate that on 23rd May 2021, we lost him due to heart attack at his residence in Mumbai. Just to brief to some of you who are youngsters about his education and academic background and his achievements. Professor Banerjee obtained his BTech degree with honors in metallurgical engineering from IIT Kharagpur and then joined BRC Trade School. And after passing from BRC Trade School, he joined at that time Metallurgy Division in 1968. And spent his entire scientific career in BERC, he obtained his PhD degree in metallurgical engineering, again from IIT Kharagpur in 1974. Maybe one of the, just after joining 6 years within joining, he got his PhD degree also. Banerjee held a visiting position of overseas, which includes the University of Sussex, Max Planck Institute, Germany, University of Cincinnati, and Ohio State University, which are USA. He got many awards. Notable among them is Satish Swarup Bhatnagar Awards for science and technology in engineering sciences in 1989. And Government of India Civilian Award Padma Shri in 2005. In 2010, University of Kolkata awarded him honorary Doctor of Science degree. He is fellow of science academies and engineering academies. He was also served as the chairman of Board of Governors IIT Kharagpur from 21st March 2014 for 3 years. He has contributed in science and academics at various places. Even I think the University of Jammu also was there for the Chancellor consultant and also at our place. Kashmir, not Jammu. In fact, he was associated in many board of governors in many universities in our country. And we lost him at quite early age, and he might have contributed much more for our HBNA, especially being academics. Nevertheless, his teaching still remains with us. With this brief welcome address and introduction of my beloved Chancellor, former Chancellor. I thank you again, all of you, for joining this program. Thank you.
Thank you so much, sir. Now it's my privilege to invite Professor U. Kamachi Mudali, Honorable Vice Chancellor at HBNI, to give his presidential remark, please.
Good afternoon. Dr. G.K. Day, the chief guest for today's event, my distinguished colleagues on the dais, off the dais, the invitees for this memorial program, ladies and gentlemen. In general, a memorial program is conducted to perpetuate the memory of the person who was so dear to us and who made outstanding contribution to the society and the community at large. And Dr. Srikumar Banerjee, I think, with the introduction that Dean HPNI gave now, is one of the outstanding personality, apart from the scientific and technological contributions, who made outstanding contributions to our HPNI, the Homi Bhabha National Institute also. So we conduct since last year the memorial program, and I'm happy to know that last year it was Professor Indrani Manna who worked also very close with Dr. Srikumar Banerjee. And this year we are proud to have Dr. G.K. Day. And I would say he is a mirror image of Professor Banerjee with respect to the scientific and technological contributions. And I think that no one else is there compared to him who worked shoulder to shoulder with Professor Banerjee for more than 3 decades. I'm very proud that he has accepted and he has come over here to give this lecture. If I recall, I think it was May 14, 2021. We had the Heavy Water Board Chairman and Chief Executive selection meeting, and myself and Professor Banerjee, we were the members, apart from Director Ajikar and our Director BRC and our chairman. And I remember the way Dr. Banerjee articulated for the next person who should be. And what a great, logical thinker and critical analysis that he made. And we could see from the way he makes the oration, you can see how much homework he would have done to speak that. He brings in beautifully the strength of the candidate, the weakness of the candidate, and then he tells that how the strength will provide opportunity to have our board and how this weakness will create some issue that how that should be managed. So we have no other option after this spellbound, the oration by Dr. Banerjee. Then I spoke next. So I have to add only the technical contribution for the next candidates, how these candidates would be outstanding for the future. And that was the last introduction that I had. And then I came to know on 23rd that I was informed that his sudden passing away, which was very unfortunate. And the person whom with, I remember my first interaction was in 1987, and he was my expert for my SOD interview. And of course, for all my interview, he was expert. And the last one, SOG, he could not come. He was in abroad, and he sent Chaitanya Kanguli as the substitute for him. So that way, that I had fortunate to, meet Dr. Banerjee in all my promotion interviews. And this is on the personal side. Professional side, Dr. Banerjee is an excellent, speaker. Anywhere his talk is there, we never miss it. Because the way he will bring in the results, analyze and give his own interpretation, and finally with a beautiful conclusion on what the study has given to him. One of the best lecture I attended in IISc, where he was telling how science can build the society in future and how the metallurgists can contribute to that. And he, along with Dr. Baldev Roy, they gave beautiful lectures on the time. That was one of the best lectures that I have attended. And Dr. Banerjee also occupied several leadership positions. I know he was the president of the Indian Institute of Metals somewhere in 2008-9. He was the president. This is the biggest body, 10,000 plus metallurgists in the country. And he was also a patron of Ferrotron Microscopy Society of India and many other like MRSI, many societies he has been associated, and he contributed to mentoring and motivating younger generation to achieve excellence in science and technology, which I have noticed, and particularly in the field of metallurgy. And officially, all of us know that he was in the highest position in our department, and before that he occupied all the positions right from the beginning. And I think he joined somewhere 1974 or so, I'm not correct, 11th batch of BRC training school. Okay. Okay, the 11th batch of the BRC training school, and 100% he devoted to the success of our department and the highest position he has occupied. I'm very proud that HPNA has instituted, is also the former chancellor of our institute, the university, and his outstanding contributions have been told by my colleague, Dean HPNA, and all of us aware that today is the day that we are trying to perpetuate his memory. We want to recall his association with HPNI and also with the Department of Atomic Energy, and that how he has steered and mentored us in making HPNI going to the next level. Very proud that this program is conducted. I am sure that in coming years also it will be done successfully. And Dr. G.K. Day has also chosen rightly a title that is role of basic research in the development of materials. I think it is very close to the heart of Dr. Banerjee. He has been always telling that any basic research should lead to finally the development of material and technology and manufacturing for making components for the nuclear industry. This is what he used to tell. And that is how that is not only that he got the highest awards in the country like Bhatnagar Prize or the Civilian Honor of Padma Shri. People should know that he got two outstanding prizes from abroad. One is, I think, the Kroll Prize. That's for the contributions in titanium science and technology. The other one is Robert Kohn, yes, RW Kohn Prize. And this is what after some stage that it's not only the national recognition, it should get international recognition. And he has been visiting faculty in Ohio State University and also visited several leading institutions and contributed to the science and technology of metals and materials, particularly in the nuclear industry. Very proud that we are doing this today, and we are having his trusted and long-time colleague, Dr. G.K.D. here to deliver the lecture. And welcome to you, sir. Thank you very much for accepting our invitation and coming over here. And we look forward to his the lecture now. Thank you very much.
Thank you, sir, for your illustrious elaboration of Dr. Banerjee's personality. So, when NAC team was to visit HBNI in June 2021 for accreditation, we had prepared a short movie on HBNI. During that time, we had recorded Dr. Banerjee's viewpoint as Chancellor of HBNI. I would like to request our IT team to play it just to refresh his ideas about HBNI.
Across a gamut of domains.
Education has been an integral part of the department's activity right from the beginning. The training school program of the department started 64 years back and is still running very strong. And this is the world's longest nuclear science and engineering education program. It can also claim that the entire technology development indigenously done in the country has come out from the work of those who have been graduated from this natural extension of this program. Those who have been working in the department for an extended period, sometimes even their entire career, they are having that experience of seeing that their own work, their own research is getting translated into the technology development in a very massive way. This is a very great feeling at the end of the career of many of the scientists who have gone through this within the department. Now that experience can as well be, at least the taste of that experience can as well be given to the students who are coming from outside to the department for their doctoral work. And that is one thing which HBNI can claim to give and which I believe no other institutions in the country, no other universities in the country can provide.
We are feeling honored to have Dr. G.K.D., a man of distinct vision, an idol of knowledge and experience, and inspiration to all of us with us today. Today's topic of talk is role of basic research in development of materials. We are very eager to listen to you, sir. Sir, you hardly need an introduction to this audience. You have made all of us proud of your distinguished work in numerous capacities in BRC as well as in HBNI and various committees in India and abroad. For the benefit and motivation of our young participants, I would like to introduce you, sir. Dr. Day obtained his BTech in Metallurgical Engineering in 1979 from Indian Institute of Technology, BHU, and he was given the University Gold Medal for standing first in the class. Dr. Day completed his PhD degree from Banaras Hindu University in 1988. He joined the 23rd batch of BRC Training School. He was awarded the Homi Bhabha Prize for standing first among the metallurgy trainees. He was a postdoctoral fellow in University of Cincinnati, USA from 1994 to 1996. He has been visiting scientist in University of Osaka, Japan, and he stood for some IFF Jeluich in Germany. He has won several awards for his scientific contributions. Of these mentions, we can make made of Young Scientist Award of National Science Academy 1989, Young Metallurgist Award given by Ministry of Steel and Mines 1989, MRSI Medal given by Material Research Society of India 2001, Metallurgist of the Year Award given by Ministry of Steel 2003, and Vasvik Award G.D. Virla Gold Medal of Indian Institute of Metals 2011, and IE Eminent Engineer Award 2012, and Distinguished Illumination Award of IIT BHU 2013. He is a Fellow of Indian National Academy of Engineering, Fellow of Indian Microscope Society of India, Fellow of Asia Pacific Academy of Materials, Fellow of Indian National Science Academy, Fellow of National Academy of Sciences, and Fellow of National Academy of Science. He has more than 350 scientific publications in peer-reviewed journals to his credit. He has served as Director Materials Group BRC till June 2017 and Rajaramanna Fellow till June 2021. Now I would like to invite Dr. Day to deliver his talk, please.
You have a pointer? Okay. Good afternoon, ladies and gentlemen. It's a pleasure to be here. And for that, I need to thank HBNI, particularly Professor Kamachi Mudali and Professor Nayak for giving me this invitation. I also need to thank Professor Dureja for the kind introduction. The title of my today's talk is Role of Basic Research in Development of Materials. When I say materials, it's not just materials, it's also components which are made from these materials. So there are a lot of steps involved after the material is produced to make it into a component. And even there, basic research can play a very important role, as this presentation will show. I would like to dedicate this presentation to my teachers in IIT BHU, who have been my guiding beacons. Some of them still continue to do that duty even today. They taught me not only metallurgy of world class, they also taught me a way of life. I have listed the names which are not exhaustive. Professor Anand Raman was my head when I was a student there, and he managed to gather a set of faculty which was probably the best which one can be gathered at any point of time. Professor Ramchandra Rao, Professor Rama Rao, and all these people don't need an introduction. And I was very fortunate to be a student of all these great professors. Just to sum up, I was at the right place at the right time because they were very young and they were together in the faculty. Later on, they grew in stature and they all went to various places. I happened to be very fortunate in that respect. I was lucky the second time when I joined BRC and I had Dr. Banerjee as my boss. And I don't have to tell you why I was lucky, because all that has just been discussed. And he continued to be my boss for about 3 decades. Third time lucky when I became his first PhD student. So with those words of tribute to my professors and Professor Banerjee, I commence my talk. This is the outline of my talk. Essentially have 3 sections. role of basic research in alloy development and product making, which is the main section where we see how basic research has been used in extracting elements, metals from Indian resources, and those have been converted into alloys and given particular shapes which can be put into the reactor. So how basic research has facilitated this, thus forms the subject matter of the first part of my presentation. Then in the second section is slightly different in the sense that I show how structured basic research by a group of people can resolve a problem like the structure of a material which has been there, but we don't know how atoms are arranged there for a long time. You can do that by structured basic research, and that forms the subject matter of my second part, because that's where we have ourselves succeeded in one such effort. In the third section, I discuss the role of basic research in manufacturing processes, because as I said, it's not just materials, we are making components. So component involves manufacturing, and even there, basic research can play a very important role. Okay, and already that expertise exists with us. All that we need to do is identify that expertise, bring them together, and apply it to manufacturing. So as I said, the first part is dedicated to making alloys and components for our own programs, and we know that we have our own resources. Unfortunately, there is no pointer, so I'll try to use this. Or maybe my hand, or if there's a stick here. Okay, fine, doesn't matter. This is the sequence that leads to the transformation of the ore to the component. The ore is mined by different agencies. First of all, it is located where the ores are by our own department, that is Atomic Minerals Directorate. It surveys the whole country and finds out where the ores of interest to us are located. And then those are subjected to beneficiation by techniques which we have developed. Please note, the ores are India specific. You cannot use the technology which has been developed abroad for the Indian ores, because the Indian ores, as I said, are India specific. The gangue material, that is the useless material which is connected with the ore and which forms the bulk of the ore, is actually unique to the country. So how to get rid of these two so that you can have the useful part? That technology we have to develop ourselves. So that is ore dressing or mineral beneficiation, and that technique we have developed. Then the concentrated ore is subjected to reduction to the metal. So here again, we need a lot of information about chemical thermodynamics, chemical kinetics, so that knowledge bank about not just about ore dressing, about chemical thermodynamics, kinetics has to be developed, and all that has been developed in the laboratories of DAE by doing basic research. So that knowledge bank has been created, and that equips us to traverse this journey. Up to here, the research in extractive metallurgy has led to the successful development of flow sheets for extraction of metals from Indian ores, and many of these flow sheets that have been successfully used in manufacturing units like nuclear fuel complex. Nuclear fuel complex makes zirconium-based components. It makes zirconium also, and that is based on the technology which has come about because of the basic research done in centers like the ARC. So that is the result of that. Also, UCIL, Uranium Corporation of India, makes uranium from Indian resources, and the process for doing that is developed in research centers like BIRC by doing basic research. So this work has been done. This is the kind of flow sheet that one develops, that is starting from the ore, you do concentration, then you do reduction, then you get the impure metal, you refine it, and you get pure metal. And this is the typical flow sheet that has to be developed for every metal from Indian resource. And that has to be done by research, which has been done. And this has been successfully created for a large number of metals which are listed here. All of these are not of interest to us immediately. But nonetheless, research was done, and this information has been made available in form of reports or publications. So based on this, you have zirconium. You already know zirconium, uranium, rare earths, beryllium, etc. Already we have plants running on these. And that is because of the research that was done here. This program was actually started by Professor Brahma Prakash long back, and then followed by Professor C.V. Sundaram, and then Dr. C.K. Gupta, Dr. T.K. Mukherjee, Dr. Suri, and so on. It has continued. So successful development of this extraction technology from Indian resources. So it has to be carried out from the scratch. Okay. Dr. Banerjee's contribution actually was after this. This is one flow sheet which you just saw, that is to get the metal from Indian resources. But once you have the metal, you are not going to use the metal. You are going to alloy it and then make a particular shape. So this is the second flow sheet that comes in. You have to make the alloy, you have to break the cast structure, and it will involve different hot and cold deformation techniques, and then you get the finished product. Okay, so here you need physical metallurgy information and also mechanical metallurgy information, which were the areas of excellence or expertise of Dr. Banerjee. He was a physical metallurgist. He studied the phase transformations that take place in this alloy. Why are the phase transformations important? Because you have to avoid the undesirable phases during this processing. You have to ensure that the phases coming out during this processing are all desirable phases. Otherwise, the component will fracture, it will break. So you have to know about all possible phase transformations. And he himself did a lot of research in studying most of the phase transformations in alloys of interest to DAE. Then hot and cold deformation behavior. What is the temperature that is suitable for deforming a particular alloy? That you need to know from research, so that you can do that deformation in the shop floor of nuclear fuel complex. So that hot and cold deformation behavior was also examined in great detail by scientists from materials group led by Dr. Banerjee. Then he created facilities for microstructural characterization, for phase transformation research, various types of microscopes, optical, scanning, transmission electron microscope. It was he who was responsible for bringing the first aberration corrected microscope of India to TFR. It's located in TFR. The first Titan microscope of the country came because of his efforts. Then for mechanical property evaluation also, he did create facilities for studying from nano level to component level, nano, micro, then at centimeter scale, meter scale, and finally component level. The mechanical properties of entire range could be evaluated in a material because of the facilities that were created because of his efforts. And we are, of course, party to all that. So I just want to give a flavor of the phase transformation work, which is his area of which was his area of strength. This is the very celebrated zirconium niobium phase diagram. In fact, this is known by people from all disciplines, not metallurgists. This is because is asked during the promotion interviews and so on and so forth. Even NPCL people know this phase diagram as well as we do. So just to have a quick recap, here we have the stable phases, alpha zirconium, beta zirconium. These are the metastable phase, alpha prime, which is the martensite, and omega, which is also a metastable phase, hexagonal phase. These are some of the phase reactions. This is the equilibrium phase reaction, and this is involving metastable phase. Okay, so here is the region where martensites will form, and if you are having more niobium, then you will have the omega phase. Now, the alloys of interest to zirconium 1 niobium somewhere here, and zirconium 2.5 niobium somewhere here. But all of them have beta phase, which can have compositions in that range, and they all can form the omega phase also, which is not a desirable phase, it is a brittle phase. So just to classify the transformations, he studied shear transformations involving martensite, pressure-induced omega, the diffusional transformation involving the thermal omega formation, beta formation, and he also studied the hybrid reactions, formation of the gamma phase. This is the gamma hydride phase, which is an undesirable phase. So in short, all possible transformations were studied by our group. We were party to that, leading to more than 200 publications for zirconium-based alloys in very reputed journals. No other group in the world can claim that they have studied so many phase transformations in zirconium-based alloys. In fact, zirconium-based alloys show more phase transformations than steels. And all that resulted in this book, Phase Transformation Examples from Titanium and Zirconium Alloys by Banerjee and Mukhopadhyay. Okay, and that knowledge about phase transformations is not just for record. It was useful during fabrication because this will tell us what are the phases that are desired and what are the phases which are not desired and how to avoid them. Okay, so that was useful for zinc alloys, zirconium 2.5 niobium, zirconium OM niobium, and zirlo, which are the alloys of interest to us, which are being used. This phase transformation information was useful while making them and while also during their use. Yeah, so this problem I had seen in the beginning, some slides are blank, but doesn't matter. So actually, the slide that we just lost is about martensite. It shows sorry about that. I did not sense that I'm not being heard by the online people, but I'm sure I'm so loud that you are able to hear me. Yeah. So, okay. See, the slide which I lost, which I'm unable to see, and I must apologize for that, is the one shows various types of martensite in zirconium-based alloys. Zirconium shows the largest range of martensites, much larger than what steels can show. And all that has been mastered to the hilt by the scientists from BARC. Here I talk of another phase, which is not a desirable phase, which is the omega phase. Omega forms from the beta phase. This is the beta lattice. By collapse of these planes, you have this, this is the omega structure, which is a hexagonal structure, not hexagonal close pack. Beta phase is BCC. BCC to omega transformation takes place in the beta, provided the composition is right. That is, if the composition is in that range, beta phase, then it will transform to omega. So we have to ensure that this does not happen because omega is a brittle phase. So this is the thermal omega, which you can get during fabrication, and you have to avoid its formation. So that is the information that gets carried on to the shop floor of the fabrication plant from the basic research. The omega phase can also form due to irradiation, and that's not good because again there's a situation where it will make the material brittle. For instance, the pressure tube. It can also form by shock deformation. We were the only people to have studied all the three types of omega. There it is thermal omega, this is radiation omega, this is shock-induced omega. Same parent phase, same product phase. Mechanism of formation, totally different. All three are totally different mechanisms of formation. Very interesting problem for people who are in phase transformation. Okay, and we have studied that in great detail, and all of them are useful. This is during fabrication, this is during use of the material in the reactor. Oh my God. I don't know what I have lost here. Okay, so let me try to recall. What was there? Well, I'm sorry, you have to bear with me. Due to some translation problem or whatever it is, some slides are lost. I'm not able to use my own laptop because of some issues. Yeah, now I remember what was the slide that is lost. The slide that is lost is on deformation behavior and texture. The phase transformation is one aspect. You also need to know how the material will deform under cold and hot conditions. So hot and cold working, the maps, the deformation maps were generated by us, and that gives information for use in the shop floor again. and also texture development, how texture will develop. For zirconium, texture is very, very important. Okay, so one needs to know how texture will develop, and on that we have done extensive studies and to show how texture will develop in zirconium-based alloys by doing X-ray diffraction, by electron diffraction, as well as neutron diffraction. So all three modes of diffraction have been used for studying texture. So now we have information about phase transformation, about deformation, and about texture development. All three attributes are required for developing a flow sheet for zirconium-based alloys. And we were asked to do that when a new flow sheet was to be developed for making zirconium 2.5 nm pressure tubes for the 700 megawatt power plants. And this work was done, this is a collaborative work, obviously, done with nuclear fuel complex and NPCI alkalines. We had a task force, and we were very proud. We had the proud privilege of being members of that. So we contributed our knowledge. For a person who is working in a lab, there cannot be more pleasure than being able to walk on the shop floor of a plant. And these were opportunities where we could see that the knowledge that we have gained during research is actually being put to use. So this flow sheet has been developed. This is a new flow sheet. It differs from the old flow sheet in the sense that it has radial forging, which is done in Ishapur as against extrusion to break the cast structure. There is increase in extrusion ratio, one step pilgering as against two with the intermediate annealing. So these are the three important changes compared to the old flow sheet. Okay, and that led to that forging and higher extrusion ratio and single cold work step resulted in improved microstructure, high aspect ratio, and high transverse texture. These are attributes very similar to that of the Canadian pressure tube. So our microstructure is now very similar to the Canadian microstructure. Earlier it was not so, and therefore we expect the pressure tubes which are being made now to remain in the reactor for a much, much longer time. And that has been possible because of the research done, and it's a collaborative effort, obviously. We have developed flow sheets of this type for many alloys, interaction with NFC and the user agency, and everywhere the basic research that we have done has been extensively useful. I'll give another example. I've just chosen two examples. I hope I do. Oh my God. Okay. Very sorry. See, I must apologize once again. I've lost two slides here, and they were on niobium-based alloys, on zirconium, niobium 1 zirconium 0.1 carbon alloys. Just to summarize what those slides had, they showed that the microstructure of niobium-based alloy, that is microstructure information, and deformation information, what temperature it will deform to make it in terms of a product. Okay. So the problem is niobium-based alloy is extremely prone to oxidation. Niobium will oxidize very quickly, and it's a high temperature alloy. So all processing has to be done at slightly higher temperature, So the problem was to find a temperature regime where the oxidation will not be very large, and you can still deform it. Our research shows that around 800 degrees centigrade, the nature of precipitates are not so bad, and you can do deformation. If you go beyond 800, some of the deleterious phases will start forming, and the material will start cracking. So that is the information which came from, that's the vital information which came from research. And that was put in development of this flow sheet. This is again a collaborative work between Nuclear Fuel Complex, Reactor Engineering Division, who are the users, and these were the fabricators and the materials group. And that led to the fabrication of these tubes of niobium 1 zirconium 0.1 carbon alloy. And using these tubes, this loop was made, and I was told by Dr. Bijayan, this loop uses lead bismuth as the coolant, for testing this high temperature material. And this loop holds the world record for the highest temperature loop, 1000 degrees centigrade. That's what I was told by the user. That's Dr. Bijayan's group in those days. Okay, so these are just two examples of how basic research can be useful for making the component, which is going to go into the reactor. You have made the component, it has gone into the reactor. Is that the end of the story? No, it is not. As Professor Kamachi will know, the deterioration starts once it goes into the reactor. Various corrosion mechanisms will set in, and the irradiation will also play a role in making it deteriorate. Okay, so you need to know what is the effect of irradiation on the material, so that you can mitigate it. Okay, what is the effect of corrosion, hydride formation, so that you can take proactive measures to ensure that your component lasts inside the reactor for a longer period of time. And so there you need another knowledge bank, that is when it goes into the reactor, degradation mechanisms you need to know, right? So we studied the effect of irradiation on 2.5 nanometer. We saw that if the beta is having high nanometer, then it forms omega phase, and that's not desirable. And this is studied not only by neutrons, also by proxy ion irradiation in VECC. VECC facility is very useful. You can use the protons there, and for doing radiation damage, very similar to that which can be done by neutrons. So neutron damage, you have to use a reactor, which is not always possible. The material becomes radioactive. It takes a very long time to cool down. Instead, you can do proxy ion irradiation, where the radioactivity issues are much less, and you can do a damage which is very similar to that of protons. Only thing is, it is very localized damage, so you have to live with that. So this is neutrons during radiation. This I told you is a shock formed material where the omega phase is formed, not desirable. This can happen during accident scenario. When there is shock pressure developed, then the material will become further brittle because the omega phase is formed. The beta phase will transform to omega, and that is not desirable at all. So that information is also there with us. Then the other mechanism of degradation is hydride formation. Various types of hydride formation takes place in zirconium-based alloys. We have mastered all the possible types of scenarios, delayed hydride cracking, and hydride reorientation on all the issues in single and two-phase zirconium-based alloys. All that knowledge bank has been developed, and that is very useful when it's actually called to solve a problem by NPCIL colleagues when a certain type of failure has taken place. One particular observation which I would like to show, this is the first time in the world where we showed that the beta phase also you can have hydride formation. Earlier it was shown that hydrides can form only in alpha phase, but we showed for the first time that hydride can form in beta phase also. Shouldn't we have our own alloys? Why you have zirconium 2.5 nanometer? Why not have something which is India specific? Well, that's not so easy, because it requires a lot of effort to prove the community that whatever alloy we have developed will sustain as well as the alloy which has been developed elsewhere. But we have made nonetheless we have made one effort where a hydride resistant alloy we have tried to develop, where the grain boundary engineering ensures that the hydrides do not form at the grain boundaries. The hydrides do form at the grain boundaries, and if you engineer the grain boundaries in such a way that you deform them in such a way, the texture is suitable and doesn't form at the grain boundary, try to form somewhere else. Now, if you put a absorber or a sink for hydrogen like yttrium, it will draw all the hydrogen in. Hydrides will not form at all. So then it becomes a hydride resistant alloy. So there was a beginning made for developing an alloy which will be hydride resistant, and it has also been published. This work needs to be taken forward further. So we have done this exercise for making the flow sheets for various types of alloys, zirconium-based alloys for reactor application. I gave you a flavor of that. Zirconium 2.5 nanometer flow sheet I just showed you. Then nickel-based alloys for heavy water plants and reprocessing plants. Niobium-based alloys, I just gave you the flow sheet which has been developed in interaction with the other scientists. Shape memory alloys for application in LCA, Tejas aircraft. This technology has been given to Aircraft Development Agency. The plant is there in Bangalore. You can see the plant from the road itself, because you will not be allowed inside. So you can see the plant from the road itself when you go from IASC to airport and so on and so forth. Many of us might have done that. This is based on indigenous technology or DI technology. Each Tejas uses 300 of the shape memory alloy rings. And now several squadrons are now flying. Bulletproof jacket, just patented and being tested by different agencies. This is also come up because of the basic research done by scientists from Materials Group on boron carbide and nanotubes. It's together, it's a composite of these two, and successfully used. It is actually, there are levels in bulletproof jackets, which this is level level 4, I believe, which can take AK-47 bullets with steel core. And that is the max that you expect in the modern environment. So this is being tested by and also other types of AK-47 bullets of a lower category this can take, obviously with much lesser thickness, and then variety of ceramic materials for in-reactor application and other applications. So this is these are the contributions where the basic research has been very, very useful, okay? And it has led to actual product development. So I just wanted to give a flavor of that, and some lessons that could be learned from this exercise is that result of strong collaboration between different groups units. This was possible because of that. You cannot do this alone. You cannot do, even one institute like BRC alone cannot do it. You have to have nuclear fuel complex as a partner and the user agency as a partner. Without that, you cannot achieve this. So collaboration is the key to success. Collaboration brings in the complementary strength of the different entities together, and the outcome is always superlative. We have seen that. And now with my experience, I tell that if, and these are all made through a task force. We have a task force where we have members from all these 3 units. We meet every month, later on every week, and check the progress for time-bound accuracy. And we have achieved very difficult targets successfully by this approach. This is product development, you know. And then lastly, very important to archive research in a proper way. It's very important to archive or record whatever you have done, you know, either in form of reports or in form of publication. Otherwise, what will happen? The next set of people, you know, they need some reference to start somewhere. They should start from where we have ended, you know, and to take it further higher. They should not start from where we had started. And that will happen if your research is not archived well. Then they will be lost and they will say that, oh, let's start from scratch. And that's not a good situation, which needs to be avoided by doing good archiving. And that we have successfully done for most cases. So that brings me, that was a flavor of research and how it can help in developing materials. I just talked about task force for solving a difficult, you know, task. Can we have the same approach in basic research for solving some unresolved issues, like an unresolved structure, you know, which cannot be solved by one person or small group of people? Can we have a task force of different capabilities of people coming together and solving that structure? Well, we did that, and I would like to present that here, you know, and this is the structure of glass. You know, if you look around us, wherever we are sitting, we have more things which are non-crystalline. Crystalline is only metals and alloys. And 90% of the research is done on crystalline materials. The remaining, we say it's amorphous or disordered and leave it, because we find that structure too complex to study. So this is one particular situation where the task force approach, which was used for making components, can be successfully used for deciphering the structure of a situation like this. That is, let us say, glass. Glass structure has disorder. That's what they say. But actually, if you look at the structure of the glass, it doesn't have long-range periodicity like in a crystalline material, but you have short-range order. That is very well known. It has short-range order. This is known for metallic glass, is also known for non-metallic glass. And many other materials which are not crystalline, they also have short-range order. By the way, that group is much, much larger than the crystalline material group. Crystalline material is a very small group, you know. And then it has medium-range order. Glass has medium-range order. And this is the order which has not been studied well. You know, and this is because of the difficulties associated. And you also have voids. You have voids here. You know, this is the structure of crystalline metal. This is a non-crystalline metal. You have voids because the density of glass is less than that of crystalline counterpart. So you have to have lesser density. And that is because of the voids. The voids are located at the end of the medium range order domains. So this is the structure of disordered materials. Because of this common characteristic, the strategy developed in this work can be used for disordered solids of all types. To study glass, you can use the same strategy for other disordered solids also. Some of the disordered solids that we know of are listed here: nanoparticles, top layers of many coatings, grain boundaries of many ceramics, glasses, amorphous silicon, metallic clusters, and so on. This list is much larger. I have only given a few here. And what is the motivation for studying this? The motivation is, if you study one, you develop the pathway for studying all of them. Study metallic glass, you will know how to study non-metallic glass, which is actually around us, in a very large tonnage and has been there for centuries. Still, the structure is not known. 2022 was the year of glass as determined by United Nations. Despite all that, much of the work with glasses, non-metallic glasses, is confined to short-range order. They don't know about medium-range order in glasses. Defects in glasses. Do you know about defects in glasses? Well, we don't know, because we don't know the structure. If you don't know the structure, how will you know the defects? Because defect is a deviation from a known structure. You don't know the structure, you don't know the defects. So if you know the structure well, you will know what are the defects. So everything is empirical so far, based on trial and error, based on speculation. Third is more important for us in the nuclear industry. What is the effect of radiation on glass? Well, for that to study, you need to know what was the structure before radiation came in. Then only you will know what radiation did to the glass. So unfortunately, we don't know what was the structure before the radiation came in. So how will you know what has happened after the radiation? That's why it's very important to study the structure of glass. And last one, glass is supercooled liquid. Liquid is where solidification takes place. You have crystals forming. So if you are able to study glass very well, you can freeze the liquid in form of glass here, and you can tell what is happening to the liquid just before it turned into crystal. It's impossible to study the liquid otherwise. But if you study the glass, you can tell what happens to the glass, liquid, when it turns into a crystal. And that is another advantage of such study. I will not go into this. Instead, I will just consider the first part, that is the structure of glass. And this is a kind of a task force approach. Well, not a formal task force, it's an informal task force where we have gathered scientists with different abilities. Short range order is one aspect, that is the first building block of glass. Short range order domains join to make the medium range order domain. And medium range order domains have voids at their end, and all three put together is the structure of glass. Okay, unlike in crystalline material, where you have just the interplanar spacing and the motif, they define the structure. One tool is enough, X-ray diffraction is enough. Here, one tool is not enough, because all three will require three different tools or many more tools. So here I have listed the tools that we have used in our study, as many as 8-9 tools. And there are people having expertise in each of these areas, and they have come forward and formed this task force to make information available. For short range order, we have XAPS, SACs for short range order and medium range order, positron annihilation for the open volume, voids here, 3D atom probe field and microscopy for short range order and medium range order. Fluctuation microscopy, this is a TEM based technique, not very old. This is for medium range order. Specialized form of filtered high resolution imaging, this is for open volume. And angstrom beam electron diffraction, this is for short range order and also for medium range order. So if you study all these aspects, you need people. I just listed the number of people involved. It can be much larger also. And this is the strength of places like BRC, where you have people of every expertise, available. And they are so humble and gentle, they are ready to contribute and come forward and interact on a platform, common platform, to solve a problem like the structure of glass. And I've been very fortunate to be part of that group, and they have successfully deciphered the structure of glass, not just short range structure, not medium range structure, the whole structure of glass. That is how these three are present. So you have cracked for the first time, in a metallic glass, and we feel the same approach can be used for other glasses also. So just to give you a flavor, I will not talk about all this because many of them are outside my domain of expertise. I'll just talk about these three little bit because these are transmission electron microscopy based. I'll first start with angstrom beam electron diffraction because this is a very new technique and it's a very powerful technique. Angstrom beam means you use a beam which is 3 to 4 angstrom in size to probe a material. you are inside a unit cell and doing diffraction. So you can find out what is happening inside the unit cell. This is very good for studying clusters which are present in the glass. So I would say it is good for clusterography. I don't know whether such a science exists. It is not crystallography, because you can study the clusters by this kind of small beam, and we have successfully done that. So this is what a angstrom beam diffraction looks like. You start from a large beam, selected area diffraction from a amount of material. Many of you, or maybe most of you, have seen this. This is a common diffraction pattern. As you make the beam smaller and smaller, you can see the changes. And when it is 3 to 4 angstrom, you get a pattern which is similar to a single crystal pattern, because now you are probing one cluster, which was not possible earlier. So you get information about a single cluster, by this type of microscopy. This can be done in a modern aberration corrected microscope. We have 10 of them right now in the country. Very fortunate to have 2 of them in DAE, 1 in TFR, and the latest one in Indira Gandhi IGCAR. Okay, so we have access to both, fortunately, and we are able to use that for doing this kind of microscopy in the country. So this is the Asgard diffraction pattern. We have assumed the structure. This is the cluster, and simulated the diffraction pattern, and you can see the similarity between the two. So this is the cluster that we are talking about, which was earlier not decipherable. So this is the building block of the glass. These clusters will join together and make the glass. Okay. So how do they join up? They can join these two clusters with edges coming together, vertices coming together, or sides coming together. This is how two polyhedra can come together. Either the vertices come together, the edges come together, or sides come together. And that information, again, you can ascertain by angstrom beam diffraction. By making the beam little larger, you get diffraction pattern from two clusters side by side, and you decipher that, and you will know how the two clusters are joined. So now we are moving from short range order to medium range order, because we are joining these clusters together. And that is what is done here. You can see the two clusters have been joined, and you get a diffraction pattern. You can interpret it, and you can tell how the two clusters have been joined. So short range order information is now being built to medium range order, done for the first time. Another tool for studying medium range order. See, medium range order has not been studied in glass, non-metallic glass at all, and that is the area of weakness in non-metallic glass literature. So we have used the angstrom beam, as well as new form of microscopy known as fluctuation microscopy. I will not go into the details. I have just shown you. I'm just going to show you what is the interesting result. This is a metallic glass, a bulk glass, a rod which is cross section. Everything is amorphous and of same composition. If you take the hardness, it is the highest here, and as you go down, it decreases. It becomes less. It becomes soft, and that is what is shown here. Hardness highest at the center, and if you go to the edges, it becomes less. So everything is glass of the same composition. So there is a difference in structure, and that difference is in the medium range order. And how do you study that? You studied that by doing fluctuation microscopy. This is a fluctuation microscopy plot from the medium in the center, which is the highest order, and these are from the periphery, where the medium range order is less. This is the only tool which can tell you why this property difference is there. We feel that this property difference is there in non-metallic glass also. You take a glass tumbler, on the wall, the center of the wall, and the edges, they will have different hardness. Never been done before. I have checked with the ceramics, but we feel certain that this is how it will be. So there is a difference in medium range order, and this technique tells you about what is the medium range order, what is the size of the medium range order domain. So we have done these two. Now we have the free volume or the open space, which needs to be determined. And once you have determined this, the bulk structure is known for the first time for any glass. Okay? So we did that again by microscopy using a new technique, which is known as filtered high resolution electron microscopy. Here, just quickly, I will tell you what happens if you have an open space or void here. The transmitted beam will get less absorbed, and therefore it will be intense as compared to the adjoining regions where this open space is not there. So absorption will not be there, and therefore absorption will be less here and absorption will be more in these regions, and therefore these regions will look dark and this region will look bright, and you have these white dots here which represent the voids inside the material. And if you take a negative of that, you see these black dots which are actually open voids inside the glass. Again, these types of information were not available before. So you know where these voids are located, and we found that these voids are located at the end of the medium range order domain. So here is the structure of glass: short range order, joined together, you get medium range order, and then you at the end you get voids. So that is the complete structure of glass done for the first time, and that's what has been said. What I just said, I will not read this out. In this study, the aforementioned sequence of information has been achieved from the same set of glass by using combination of techniques. So this is a combined approach of about 12 to 15 scientists who have contributed together, not in a formal task force manner, but an informal task force manner, having different capabilities to resolve the structure of a very common material which is there all around us, but we don't know the structure, that is glass. Okay, the same aforementioned methodology can be used for studying the complete structure of non-metallic glasses and a variety of other disordered materials. Okay, now we can do computational material science on glass. See, computational material science was earlier being done only crystalline materials because we knew where the atoms are, and that is how you could develop a material, crystalline material, from first principle. Now you can do that for glass for the first time. That is the strength of this study. This is the last slide in this section. Before I move on to the last section, is it proper to call glass as disordered? In my view, there is no disordered material. We just showed you that there is the so-called disordered glass also has short range order and medium range order. It's not totally disordered. So there is nothing like disordered material. It's better to call such materials as partially ordered or differently ordered rather than calling them disordered. You can put them in a general class of non-crystalline materials. Non-crystalline is all right, but disordered is not all right because there is nothing like disorder. You have short range order, medium range order. So how you can call it a disordered material? Okay. So with that, I come to the last section of my talk, where I show the importance of basic research in manufacturing process development. Many of us, including me, I was involved in so-called basic research. And often we found this criticism that how useful is this research? You're just publishing papers and so on and so forth. But all that information generated from basic research, if you put it in a particular way, you can actually use it very effectively in manufacturing or improving the existing technique of manufacturing in a very systematic way. And my last part shows one such development which we have done together. See, this is the first wall of the test blanket module. As you know, in the fusion program, 7 entities are contributing. India is one of the entities, and the fusion program required that we make the first wall of the TBM, test blanket module, which was to be supplied by India for incorporation in the reactor. And this was a very big challenge. First, the material was a challenge. Material problem was solved. The RAFMS, reduced activation ferritic martensitic steel, was developed because of efforts of our colleagues at IG CART, and that technology was transferred to Midhani for production. The material problem is solved. How do you make this? It's about 1.6 meter long. This 0.5, and this 4 or 5 meter, 0.445 meter, length. So if you have it in form of a sheet, actually these slots are extending right through 1.5 to 1.6 meter length slots of uniform cross section. How will you machine it? That is the challenge. So in foreign countries, they are making it in two halves. This half and the inside half, the outside half, they are joining it together by hot isostatic pressing in a large hot isostatic press. We don't have such a press with us, number one. Number two, the joint made by this process is weak and compared to the base material. Okay, so it will crack up. It may crack up during use. Whereas this has this is a solid monolithic structure. There are no weaknesses, and you have these channels made by EDM, electro discharge machining. This work was, this activity was led by Dr. Sujay Bhattacharya, and this activity later on became the part of his PhD program. So where is basic research in this? This is all an engineering problem. You've done EDM and you have succeeded in making a large component successfully for the first time in the world. All that is fine, but where is the basic research in it? The basic research comes in when you look at the surface, the machine surface, in the SEM. This is what you see. You see craters in it. You see cracks in it. Though this surface and this component is acceptable in all respect, in fact, many of the other things, that is around us, if you start seeing in the SEM, you will see features like this. So don't get alarmed. I mean, they will still do the function. But, I would like to make it more smooth. So that's where the basic research comes in. So we would like to know how these craters form, how actually EDM takes place itself, how the EDM process takes place. Then only you can improve it further to give a smooth surface, So EDM is actually a machining technique where you remove materials by using spark radius produced between two electrodes separated by a dielectric. Intricate geometries can be machined with an accuracy of 0.005 mm. Plasma is created during discharge, which melts the workpiece, and continuous flushing of dielectric electrodes the molten material. So this is the schematic diagram for EDM. You have the two electrodes. One of them, of course, is the material itself, and you have the melting and removal of material. So local melting and removal of material. And you have the material coming out in form of droplets. This is the plasma which is created here, and you can observe all this because of the high-speed photography capability existing with us. These are the process variables which are listed here. You can change them, tweak them to create to change the actual appearance of the surface. So this is the basic process that the way it takes place. So here you have several things happening. The plasma. So we have expertise in plasma here in BRC. There are groups who are actually mastered this technique. So if you can bring one person from that group to look into the plasma develop, then interaction of plasma with matter. That is the second area where again we have experts which are around us. High speed photography, again expertise available. And finally, modeling this whole process. Again, fourth group of people, all this expertise is available. So if you can bring all these together and sew these expertises together, you can understand this process the way it has not been understood before. And you can also create a very smooth surface. You can remove all the large craters that were present during machining. So that was the objective of this. So this is the way the crater looks like. When you do just one crater formation, this is a stainless steel. This is in P91, which is the material which was chosen for the test blanket module mock-up. This is in zircaloy and this is in copper. So the appearance of the craters are different because the material property is different and the energy imparted to these processes are also different. So the temperature generated during this process are listed here. 8,000, 14,000, 6,000 and 10,000. So there is melting and even there is evaporation. Quick melting and quick solidification and removal of material all taking place together. So what is happening is not only craters are forming, the microstructure of the top layers is getting completely changed. Because of this melting and solidification, you have completely new microstructure on the top, and therefore the properties will be very different from the base material. That is another area of concern. So you have surface roughness, you have cracks, lengths of those are important, crack orientation, residual stress, and of course hardness. So this is one such cut surface of P91 made by high energy. We have seen this surface on the plan view to get an idea about the nature of the crater, the size and so on. We have also examined the cross section to see how deep is this effect. And we found that the top layer, of this here, when we did electron microscopy, we found that is amorphous. Local glass has formed. That would mean that it's not only melted, it has cooled very fast to get you a glass, amorphous layer. So you have amorphous layer on top, and that will have a different property compared to the base. This is with high energy input. With the low energy, you can see the change in the surface. Very smooth. So normally one would not do studies like this. We have done these studies and told that how change in the energy can lead to change in the appearance of the surface by doing extensive studies. So it will tell you not only how to change the energy for getting better surface, this will also tell you how to keep the microstructure not so much different from the base. If the microstructure is very different, then your surface will behave totally differently from the base, and that you don't want. I don't know what is lost here, sorry. So just to show you the simulation, the whole thing has been simulated. This is the crater which is being simulated here, 35 micrometer. We take the heat input and the thermal conductivity of the material and simulate. This is by modeling. You can see the diameter of the crater, 1/4 of the crater diameter, and compare it with the actual crater size. So it will tell you, the simulation will tell you that what will be the crater size if you have the materials property and energy input together. And it will also tell you what is the cooling rate. So if you know the cooling rate, you will know the microstructure completely. And if you know the crater size, it will tell you the surface smooth, finish, surface roughness. So both these things can be determined by modeling also. And therefore, the research will tell you what will be the finished surface condition by this technique. So we did this not only for P91, which is the this thing. We did it for zirconium, also zircaloy, sorry, materials of interest to us for with this one stainless steel and aluminum, again alloys of interest to us. And now we know we don't have to do any trial and error. Normally what happens is you will do trial and error and find out what is the condition which will lead to a good cutting smooth surface. We don't have to do that. We just feed the material property and it will tell you what energy you should put to get a smooth surface. So that is the outcome of this exercise, where the basic research inputs have been used for mastering the understanding of electrodischarge machining so that you get a smooth surface with the desired microstructure. So here you have plasma generation information from one group of people, interaction of plasma with materials, another group, and modeling, third group. If you sew all this expertise together, you understand an important engineering manufacturing technique the way it has not been understood before, and you can apply it directly to the shop floor. So this is an example where different components of basic research, if you can sew them together, you can understand a much bigger manufacturing problem better. You can tweak, you should be able to, then you'll be able to tweak it in such a way that it will give the desired results. You can even develop a new machining technique. We have applied this not only for machining, we have also applied it for friction stir welding, where we have done modeling and we have shown that these are the conditions which will give you the best joint by modeling, for similar as well as dissimilar. So we can apply it to other fabrication techniques, other cutting and joining techniques, this type of approach. And this approach can be very successfully applied to other manufacturing processes as well. So that was my last slide. And I would like to conclude by making this statement. This is more for my own absorption. I could achieve much more as a member of a group, be it science or technology, rather than as a lone crusader. So this is, if I don't think I am senior enough to give a message, but this is what is my summary of my learning during all these years of research, that alone you will not be able to reach very high, in terms of both science and technology. However, if you join with right minded people having different capabilities, you can probably do wonders, and that is possible more so in the DA institutes where we are all part of. So with those words, I thank you for your kind attention and patience. Thank you very much. And sorry for the missed slides. Well, I don't take the blame entirely on me. I have my in my laptop. Unfortunately, I was not able to connect my laptop. Yeah, sure.
If anybody has any questions, please.
Yeah.
Sir, thanks for, as usual, a great talk. And as I mentioned to you that for me, it is important that I listen to people like you regularly. So one or two short questions. One is that this omega transition induced by three variables: temperature, pressure, and radiation also. At a glance, I could see from structure that parent phase has got 4 planes. Omega has 3 planes. So 2 planes maybe collapse and you get 3 plane omega phase. I can understand by pressure, also by radiation, but temperature and pressure are supposed to cause opposite effect. But even then, we get same product.
Yes. So the mechanism is different. See, when I talk of pressure, no, it's shock pressure. It's not isostatic pressure. Isostatic pressure also omega forms. In zirconium, it forms. You get omega phase by a lot of work done by Dr. Sikka, Dr. Chidambaram, and
Yes.
others. It's very well documented. This is beta phase. We are talking of omega and beta phase, and the morphology is a plate-shaped morphology. It is a shear-induced transformation. Totally different mechanism compared to the mechanisms which were taking place elsewhere. So you are right. This is a very interesting situation.
Yes.
And all omega experts, they are very intrigued by seeing
Yes,
this
yes.
behavior.
Yeah,
That
no doubt.
same parent, same product, but
And three different,
totally different morphologies.
Yeah.
And we have stood to some extent, understood to some extent, and it's documented in the publications which are connected with these three. And as I said, unfortunately, it's undesirable transformation for us. The first one, thermal, is during fabrication, during the in the flow sheet, on the shop floor. The remaining two during the use.
One more short question.
Yeah.
Once I was telling with Vyas sir, our immediate past chairman AC. So he was asking, just we were discussing a topic like how to strengthen zircaloy. So I said ki how we have research going on ODS steel. Can we also have ODS concept in zirconium based alloys? So any such effort is underway or it is not possible or not applicable?
See, in principle, you can strengthen zircaloy by oxide dispersion, but then it will lead to many other undesirable things.
But that is true for SS also.
Yes, it is true. See, that's why I'm saying that oxide ODS materials have, I mean, I can be criticized for this answer, but the fact is that ODS has not found great application yet. And it is because of there are so many other issues connected with the ODS. Oxide dispersioning is not, it's not a medicine for all ailments. So we should look into other methods of strengthening without compromising the other properties.
Like I read papers where they say in SS, slight anisotropy appears. So these kind of negative things are also there.
Yeah, definitely. See, I would, if you give me the preference, I will not probably go the ODS way. Because
even for SS also.
See, even for SS also, because a lot of research has already gone by very prominent people, and it has not really led to some major breakthroughs. And it's not easy to make ODS. It's not easy to make ODS components.
In fact,
he knows he's been
in fact, here I may
and my colleagues in NFC, they struggle a lot. You also have to involve probably ARCI and so on. So it's not easy.
Yeah, here I may refer to his work, our Honorable Vice Chancellor's work, nitrogen containing SS.
Yeah, I see. That's the point.
You can take.
Why I will go for ODS? Why not have other alloying additions and solve many of the issues? And that doesn't lead to other problems. That doesn't lead to other problems. So that's the beauty of the other routes which would like to prefer. This is just another route in that direction.
That's very very nice that the nitrogen effect has been taken up. But I have a another interesting point. Today we all talk about hydrogen storage materials and hydrogen storage systems. When you talk about this disorder structure to partially ordered or anything, I think that will have a great message for hydrogen storage.
Yes, it will.
I don't know how far, because I'm saying this is very interesting point, particularly after doing the.
See, I am a non-metallic glass material scientist.
Yeah, I worked on the bulk metal.
Yeah, I know that. So you will understand the see, I'm a metallic glass material scientist like you. The non-metallic glass community is far more strong. It is lakhs of people across the world.
Yes.
And when I asked them, I was a chairperson in a video conference which was being done in CGCRI.
Okay.
And probably the second most prominent person, or maybe one of the most prominent person in non-metallic glass, he was giving a plenary lecture. And at the end of the lecture, I asked my harmless questions, and the answers did not come. Like, what is the medium range order? What is the defect?
Yeah.
How do you see what is the effect of
This is a
radiation?
great message.
So,
particularly with
and
respect
no,
to
it's not just a message. I'm glad that we are able to evolve a
the
technique
technique.
for understanding the structure of this kind of disordered solids. So I hope there will be bias and we'll be able to take it forward.
No, I don't know whether Divakar can speak. He is in the online.
Divakar knows about work. He's a colleague. I must thank Divakar for permitting. He's a group director now. Permitting his colleague to interact with me. Divakar, we were together. I mean, I taught him in tennis school also. So we just met during our PSG interaction, and very kind of him to permit this interaction. And that's the beauty of DAE.
Yes.
Retired person like me still has some takers. So don't make them afraid.
Thank you.
So,
Thank you.
Martensites. So what do we mean by different type of martensite? Is it compositions are different?
No, composition. The morphology is different. Morphology means if you look at the microstructure, there are essentially two types of martensite: black martensite and plate martensite. And one is twinned and the other is dislocated. Okay. So the internal structure is different, and they form in two different compositions. So that's all very common in steel. The same thing can be seen in zirconium-based alloys also. And in fact, more variety can be seen in zirconium-based alloys.
Okay. And sir, one little doubt I have. I just want to understand physically what it means when I say that we now know the structure of glass. Okay, so short range order means I know the nearest neighbor. Medium range order means I know the next nearest neighbor.
Yes, one nanometer. Up to 1 nanometer. See, that is the stumbling block in this whole gamut. The medium range order information. There are no tools for studying the medium range order. It's not crystalline. You will do the microscopy, you will get nice images and so on. It's not crystalline. So that is where the recent contributions are coming in that. That is how to get the medium range and order information. New techniques like fluctuation electron microscopy have been developed. People are using synchrotron for and along with reverse Monte Carlo for simulation and getting better idea about medium range order. Yeah, continue your question.
So then you said we know short range order and we know that there's a medium range order and then there is a void to it.
There's open space because you see the medium range order cannot extend very far. Otherwise it becomes long range order, which is not the attribute of glass. Glass lacks long range order. So medium range order will definitely break down because the way the medium range order is. And when it breaks down, a new medium range order domain starts.
Okay.
So between them, we have some open space. That is where the open space is located.
But that medium range order and the other medium range order that I'm seeing, they are similar.
They have to be similar in the same material, having the same composition. This is a very good question, and that is the case.
Okay.
They are similar. The size may differ a little bit, but not much. See, these are the informations which are coming out now. And if you delve slightly deep into it, then questions like this come. And they are exactly same. They are exactly same. That is characteristic of that glass.
And one silly question, sir.
And it changes when you change the cooling rate, by the way. It changes when you change the cooling rate, and that leads to the difference in properties.
Okay. And that empty space between one medium range order and the second medium range order, will that also be constant?
That also be
same?
Slight difference in size. Our technique, we have seen slight difference in size, not major difference in size. A slight difference in size is there. This can be detected by positron also. And we have seen it directly in the microscope, filtered high resolution microscopy.
Thank you, sir.
Yeah. 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 Yeah, right. Yes. The modern tools that, especially the aberration corrected microscope, can do wonders with these disordered materials. And as I said, these disordered materials form the bulk of materials around us. We don't bother to study them. We just use some empirical approaches. We just trial and error method, and then but that's not the actual science the way it should be.
Sir, first of all,
Banerjee, madam.
my sincere homage to Professor Srikumar Banerjee, sir, because of whom we are listening to you today, sir. My questions are number of, sir. We start with a dissimilar metal welding of zirconium.
Yeah,
as
what I forgot to mention is about her domain of work. They are also this modeling, it can tell what conditions to use to get the best joint. So that's again basic research leading to an application. So that's I forgot to mention. I should have mentioned.
Yes, sir. So please tell me the challenge between zirconium to SS welding, sir. Zirconium 2.5 niobium to SS welding, sir.
Oh, SS. See, when you weld all this type of material, there will be by the fusion techniques. There will be a lot of intermediate phases forming.
Yes, sir.
And intermetallic compounds which
Yes,
are
sir.
brittle.
Yeah.
So it will make your joint very, very brittle. And in most cases, that is the major problem. So they put various types of interlayers and do diffusion bonding. That is one. The other technique is yours, where the process is so fast that there is no opportunity for making these intermetallic compounds. The conventional fusion weldings, what happens is we allow a lot of time for these intermetallic compounds to form. In fact, we will need to conclude that part of the work where we have to tell how exactly. A lot of interesting things, still not proved by people, and there's scope for contribution. Yeah.
Last, sir, this residual stress, sir, how to get relief?
Oh, I wish there was such a easy recipe which I could have told you right like this. See, residual stresses, you have to see stress relieving occurring not in a one single step. You have to make the process such that as the stress build up, they get relieved also. So it's not easy to do that, but one has to look at the process more intricately, and that is where the information coming from basic research can be useful. For instance, here also, the EDM cutting, residual stress is one of the factors.
Yes, sir.
Because it accumulates on the surface and leads to this crack formation, which we don't want. And so we have to see that how these cracks are forming and what changes in the conditions that you want to make so that the cracks are less. And unfortunately, I could not present everything. As I said, it is Dr. Sujay Bhattacharya's thesis work, and he has done it very well, and the work was very much appreciated even by the examiners, because it starts from basic research and contributes to actually a machining problem in a major way. In fact, Dr. Banerjee was the doctoral committee chair, and he was very, very appreciative of this work.
Last question, sir, for electron beam refining which we are using, how important it is to have uniform heating in that process, sir? Uniformity of melting process.
Uniformity of melting process is desired everywhere. The problem is uniformity is not always easy to get. Right. Electron beam melting, since there is no stirring, unlike in induction melting where there is stirring, unless until you make some arrangement for mixing of the molten pool, the uniformity will be slightly difficult to achieve. Okay. That is what is the general experience that we have, and that is why we look for induction melting. Wherever we can apply induction melting, we will right away like to go for induction melting. But unfortunately, it cannot be applied everywhere.
Thank you, sir. Yeah. Thank you.
Oh, you also.
In one of the slides, you have mentioned that the center portion of the dye is so hard, but it is prone to easily for corrosion. Whereas the end portion is this
right.
seems to be contrary.
Yes, no. See, central portion is ordered, is more ordered because it cools slowly. It gets time to get ordered. So the medium range order is the highest there. It's very similar to the crystalline arrangement, and the crystalline arrangement has less corrosion resistance. than the amorphous alloy. Okay, so the peripheral region cools very fast and therefore is disordered, and should not use the word disordered. It has less medium range order, and therefore it is more resistant to corrosion. Because you don't have non-uniformity so easily, whereas here you will have non-uniformity.
The general question is a more general. Whenever we do some research like this, sometimes we used to end up in accidental results. So, in your experience,
you are talking about accidental good results or accidental bad results?
Anything, sir. Any experience?
Yeah, both can happen.
Sometime,
yes. And both are new.
Yes. Will it lead
so,
to some other?
I consider that even the bad, the so-called bad, the rest of the world needs to know, so that nobody will go that way, isn't it? So, I consider both of them equally important.
Any accidental discoveries that leads to something
accidental discovery means here the fact that we located the voids at the end of the medium range order domain, that is, I think, the key to building the whole structure. And that part was not known at all. In fact, much of it is not known because nowhere so many people have come together to work on one sample. People have one area of expertise, he uses that and solves one aspect of the structure. But that is not the whole structure. In a crystalline material, that could have been the case because there is a motive when it moves around and you know the structure. In amorphous, that is not so. So you need to bring a large group of people together, and that's the advantage of a place, as I said, BRC or IGCAR, very knowledgeable people, very humble people, down to earth and ready to interact. So very fortunate to be associated with such people. Thank you.
So after you establish that there is order in the glass, how to define the glass next time we talk about glass?
Okay, glass. See, this is a very good question. Not so easy to answer though, because there are so many things which traditionally they have been said. Nobody will believe that this is not disordered and so on and so forth. We can call it partially ordered or differently ordered. That's my suggestion. Because I will not accept the word disorder. I'm trying to avoid using this word disorder because I know that there is nothing like disorder. Randomly ordered. See, random word is also little. No, gas doesn't mean disorder. That's what I'm trying to say. Glass is a viscous liquid. When the liquid viscosity of the frozen liquid, I'll put it that way. Sugar full liquid. Okay, so that is the way I'll put it. Okay.
If there are no more questions, thank you so much, sir, for your enlightening presentation on role of basic research in development of materials. On behalf of HBNI, I would like to request our Honorable Vice Chancellor, sir, to hand over a memento to Dr. Dev, please. Please accept it with a sincere thanks, sir. Thank you so much, sir. I would like to request our Registrar, Professor Selvan, to propose vote of thanks, please.
Those we love don't go away. They walk beside us every day. Unseen, unheard, but always near. Still loved, still missed, and very dear. This is the ways we can still memorize our Srikumar Banerjee. I here stand by for proposing the vote of thanks. If you don't invest in basic research at some stage, you start losing the basis of applied research. Science or research is always under pressure to deliver something which can be used immediately for society, says Rolf Peter Heyer. Good evening to one and all. First of all, I thank Dr. Gautam Kumar Dey former director, Materials Group BRC, for his extraordinary and informative lecture on role of basic research in development of materials. As a dedicated teacher, he presents all the slides and explains in a systematic way. And the beginning itself, our Vice Chancellor has made is a mirror image of Dr. Srikumar Banerjee. And he is proved, the youngsters could not see Dr. Srikumar Banerjee. I think now we realized how great he is through the lecture of our resource person, Dr. Gautam Bade. He has made his research beautifully on these three topics: role of basic research in alloy development and product making, role of basic research in understanding the unsolved structure, role of basic research in manufacturing and process development, with beautiful slides. Yes, sir. I think with your elaborative speech, we understood that we have to open maybe a new kind of term, the clusterography. And very many things, whenever I used to be a teacher, I used to say the glass materials are short range ordered and crystalline materials are long range order. One of the students asked some time back, "Sir, can you say anything medium range order?" Then I said that, "Fellow, don't be silly like this." Now I realized that these medium range order materials can exist and that can lead to wonders. So I think having a topic of clusterography, I heard this is the first time. Maybe in future, a new branch of science may arise with this. So thank you very much for your enlightening talk, sir. I would like to thank our Honorable Vice Chancellor, Professor Kamachi Mudali, Professor P.D. Naik, Dean HBNI, Professor A.K. Dureja for delivering their presidential welcome and introducing the chief guest. I thank all the people who have joined through online, especially Professor Grover who has joined there. Thank you all for joining us through online. It's my honor to express my gratitude and recognize the efforts of those who diligently work to make this function a grand success. My special thanks goes to Professor A.K. Dureja for organizing this event. Finally, I'd like to thank all of you who are present here for making the time to be with us today for the lecture and helping us to make this event a grand success. Thank you, one and all. Jai Hind.
Thank you, everybody.